Hi. So in today's lecture, what we're going to do is basically take the ideas of using metric spaces in approximation algorithms a little further. Okay. So last time, if you recall, what we had seen was the following, that many of the problems that arise naturally in approximation algorithms, especially the ones related to cuts and graphs, can be viewed as problems occurring in some metric space. Okay. In this context, cut metrics were this important class of metrics which put the distance between 2 points or two vertices in the graph as 1 if they were on opposite sides of the cut, and 0 if they were on the same side of the cut. And by relaxing this notion of cut metrics to be a general metric, we could write out LP relaxations and design rounding algorithms for them. Okay. Now, already this gives you some idea that cut metrics are kind of hard to optimize over directly, and which is why we had to move to a more general class of metric spaces and work with those. Okay. And this idea of easiness and hardness is what we'll build on further today. In particular, we are going to see how we can start with a problem which is formulated in a so-called hard metric space and try to kind of map that problem to a similar problem in an easy metric space. Okay, and try to solve it or at least approximate the solution. Okay, so with that, let's go on to today's lecture. Now, the easy metric space, so to say, that we would want to work with in today's class is the class of tree metrics. Okay. Now, if you recall, we had seen what was a graph metric space. Okay, so given a graph undirected G comma E, possibly weights on the edges. Okay, we had defined a metric space associated with this graph where the X or the set of points was identified with the vertex set on the graph, and the distance between any I comma j, where I and j are points in X or equivalently vertices in the graph, is the shortest path distance in G. And we had seen that this is indeed a metric. Now, a tree metric is a graph metric, but where the graph is actually a tree. Okay, so we'll usually use T for denoting tree metrics. When T is a tree. And why are tree metrics useful? Now you can always already guess why this might be the case. Many problems are much easier on trees than in general graphs. Okay, so for instance, if you just take your shortest path problem, if you look at the shortest path between 2 points in a tree, it's really simple because there's a unique path between the 2 points in the tree. Okay, so you really can't go wrong if you take that path. Whereas in a graph, you actually have to compute the shortest path. Okay. Similarly, other problems that you have seen, including TSP, K median, and even things like vertex cover, are easy on trees. Okay, so you can find polynomial time algorithms for these problems on trees. So the question that you might want to ask is, especially for problems like TSP or K median, where the problem itself is formulated in a metric space, you want to ask whether is there a tree metric space close to the given input. Okay, so is there a tree metric space in which the distances between points look like the distances in the given input space? If yes, then one possible way of thinking about or going about solving these problems would be, well, solve it on this tree metric space. okay, and then somehow map back the solution, because it's really easy to solve it in the tree metric space. So you map back the solution to a solution in the general metric space. Okay, and of course you will lose some factor in mapping this back possibly, which is where your approximation factor will come in. So this kind of motivates the following question. Given a metric space M, which is x comma d, is there a tree metric space x prime d prime such that there is a mapping from x to x prime, the distances between I and j is approximately equal to the distances between f of I and f of j. Okay, so what do I mean by this? This is just saying that here's my original metric space of points, which may be general distances. Here's my tree metric space. So you want to map points on this to points in the tree metric space so that the distances are preserved. Now let's see this in action with a simple example to clarify the concept. So suppose my original metric space was this graph, was specified by a graph on 3 vertices which form a triangle. Okay, so d of AB is equal to d of BC is equal to d of AC is equal to 1. Okay. Now, is there a tree that can exactly reproduce these distances? Well, not really. If you see that the only possible tree on 3 points is a path. Okay, and if you want to reproduce however I label it, say I label it A, B, and C. If I want to keep this distance as 1 and this distance as 1, in this tree, we have distance between AC is equal to 2, which is not equal to the distance in the original metric space between A and C. It looks like you cannot find a tree that reproduces the distances exactly. Okay. At least not, but there's a small thing that you can do. Consider the following tree where you introduce one new vertex. Okay, so you've got A, B, and C. Okay, and then you introduce a dummy vertex D, and then you set all of this to be equal to half. So here you have a tree T prime such that the distances between the points A, B, C in T prime is equal to the original distances. Okay, so there's a mapping between this metric space to a tree. The only caveat is that you have one extra point in the tree over the number of vertices, which is usually fine for most cases. Okay. But notice that even in this particular case, the distance between A and C is not very far off from the original distance. It's a factor 2 away. Okay. Now let us see an example of a set of points which cannot be mapped to a tree metric at all. Okay. So you just take the square. You have 4 points. Okay. And so the distance between A and C is equal to 2, and the distance between B and D is equal to 2 when all of these distances are equal to 1. Now can we map it to a tree? Now if you think about this for a bit, you will see, okay, let's try out our options. Suppose I set A, B and C as before. Okay, so you get the distance between AC to be equal to 2, which is exactly like in the previous graph over here. But then what about D? Okay, because you want the distance from D to both A and C to be equal to 1. But then you cannot connect D to both A and C over here with weights 1. So that would be an issue. Okay. Similarly, if you try the trick of this side, that is you introduce this extra vertex and then you write this as A, B and C, already this reaches a problem, because let us say these lengths were L1, L2 and L3. What you want is L1 plus L2 is equal to 1, L2 plus L3 equal to 1, but you want L1 plus L3 is equal to 2, which seems to be impossible unless you have the middle L2 to be equal to 0. Okay, and of course this does not make sense, because ideally you might want this or an edge connected to it to be equal to D. Okay, so you think about this for a bit and you can convince yourself that you cannot exactly map this original metric space M into a tree T, okay, while preserving the pairwise distances. So you can actually show, in fact, that if you take a n cycle and a metric based on that for n large enough, okay, and you try to find a tree that resembles the distances as close as possible to the n cycle, uh, you cannot only not find a tree that uh, resembles the distances between pairwise points exactly. In fact, the distances will be distorted, that is, the distances will grow by at least omega n. Okay. So it seems that there is no simple way to look at this example of a cycle metric as being close to any tree metric. And this is where we will introduce the notion of randomization, because while a cycle metric may not be exactly equal to or close to a single tree metric, we can consider randomized distributions over trees. So if you look at your given metric, which is the n cycle, let us take the 4 cycle that you have seen before and look at that as being 1/4 of combination of 4 trees. In fact, these are just paths over here. Then what can we say for the distance between any two pair of adjacent points? In fact, this will also hold for non-adjacent points. Um, so let us just pick AB in the original. Okay, so D of AB is equal to 1. Okay. And now if I look at a uniform distribution over these 4 trees, what is the expected distance of AB? So the expected value of D prime of AB, where the expectation is taken over a random choice of trees. Well, notice that the distance between A and B in this tree, which is randomly chosen from one of the 4, is equal to 1 with probability 1 minus 1 over n, because there is only one case, which is the last one, in which A and B are separated. But when they are separated, they get separated by quite a bit. Okay, so the distance between A and B over here is something like n minus 1 times. And but the probability of that happening, of A and B being separated by a large distance, is only 1 over n. Okay, and this is less than equal to 2. In fact, it's 2 minus 2 over n. So what this means to say is that if I choose a random path or a random tree out of these four, then for any given pair A and B, uh, the distance in the original graph, which is the original cycle, is within a factor 2 of the distance in the tree. And the way we have set up these trees, it's always true that d prime of AB is greater than equal to d of AB. Okay, so here it's d and here the distance is d prime. So this idea is going to be the key idea in which is what we'll use in solving the problem which I'll introduce later for today's lecture. Okay. So the other thing to note is that we really did not even need to introduce extra vertices into the trees in order to make the distances match up approximately in this randomized setting. Now, this being said, let me now go on to introduce the more general definition of embedding of metric spaces. So what you have seen above is an embedding, what is called of the n cycle into a distribution over trees. Okay, in other words, this is also represented as n cycle embedding into tree, okay, or rather, more specifically, it's the metric. So what you're looking to preserve is the pairwise distances between points. Okay, and we are preserving it in this expected sense. Okay. Now, more generally, you can talk about embedding a metric space xd into another metric space x prime d prime via map f. And what do I mean by this map being a good map? It should have, okay, let me write it this way: f embeds x comma d into x prime comma d prime with distortion delta. That is, I want to formalize the concept that the distances in the new metric space are at most a factor delta off from the distances in the original metric space. Okay. If you have always that the distances do increase in the new metric space, d prime of f of I comma f of j is greater than equal to d of ij in x, and b, you want of j is less than equal to delta times distance between I and j. So this is a deterministic embedding, and if you had a randomized embedding, then you would have an expected value over here. So I hope the definition of this distortion is clear. Of course, you again just need to keep in mind the example that you have seen above. to know what this means. Now you might pause for a moment and ask, why do we want a condition like A? That is, why should the distances in the new metric space be at least the distances in the old metric space? This is not really a strict condition. What we want is that the maximum stretch to the maximum shrink should be at most delta, but the fact that distances increase is without loss of generality. Okay, by without loss of generality means that okay, so it is sufficient to look at maps of this form where the distances always increase. Now, this concept of embedding between metric spaces that I have discussed is not just important to approximation algorithms, but it's a much more fundamental mathematical concept that also turns up in various applications. Most notably, if you look at machine learning situations where you have input vectors which are feature vectors for the space being learned lying in really high dimensions, then it's really difficult to run these complicated machine learning algorithms on them. Okay. However, you will notice that many of these algorithms just depend upon the pairwise distances. For instance, if you take up clustering problems, like variance of k-median, which is the k-means problem, a really famous problem, it only depends upon the pairwise distances between the points, right? And so instead of working in my original d-dimensional metric space, you would look for some sort of dimension reduction. Okay, that is, you have a set of points in d-dimensional space, but d is very large. So all your computational aspects which are running on it take a long time. Turns out that you can actually map this or embed this and I'm talking about Euclidean points. Okay, you can embed this in just a log n dimensional space such that the distances are preserved up to some epsilon factor where epsilon can be as small as you want. Now this is called the Johnson-Lindenstrass lemma. Okay, and it's a really important result that is used all over the place usually. Okay. Now, let me state a really remarkable theorem regarding embedding of metrics into tree metrics, which is what we'll use for today. So, if VD is a metric space, such that V of UV is greater than or equal to 1. Note that this is just a scaling factor because you can always scale up distances to satisfy this. And of course, here I mean U is not equal to V. Then there exists a randomized embedding into trees. So you get V comma T prime where T prime is random such that, well, the distances in this new metric space is greater than or equal to the distances in the old metric space. T, the expected value over T prime is less than or equal to, and this is the crucial factor, order log n times the distance in the old metric space. That is, distances do increase in the new metric space of the tree, but they don't increase by too much. Okay, and the second thing to notice is that the input and the output metric space have the same point set. That is, the points have not changed. You don't have need to add dummy vertices into. Now I'm not going to give a proof of this in this lecture, but you can find a partial proof that gets to, I think, order log n divided by log n in the textbook if you're interested. Now, another noteworthy aspect of this theorem is the fact that the metric space v comma d can be any metric space. Okay, it need not necessarily come from a graph metric. It can be a cut metric. It can be the L2 metric, a finite set of points, and still it is always log n close to a tree metric. That is, in a randomized sense, you have a distribution over trees and you pick any one of those tree metrics in expectation a point pair in your original space is within log n of the point pair in the tree space. So let's go ahead and use this embedding technique to solve a problem. And the problem for today is the buy at bulk network design problem. Now, in the buy at bulk network design problem, the input is a graph which has lengths for every edge. Okay. Now we'll come to why these lengths are needed in a moment. Now you also have k sourcing pairs, uh, and the goal is to kind of, in some sense, route demand di between the SI-TI pair. So think of this as being some sort of a network of cities, and you want to have at least so much bandwidth to go between source city and a destination city in the graph, which is Si and Ti. You need Di amount of bandwidth on that. And so you need to figure out on what edges, how much do you need to buy. Okay, so suppose you say that I want, okay, so now I need to route between city A and city B Di units. Now I choose a path to route this, right? And this path, I need to put at least Di amount of bandwidth. Okay? So here say S1 and T1, and to route this I use the path, and of course you needed to use at least di amount of bandwidth on this cable. Okay, now suppose you had S2 and T2. Okay, now to route S2 and T2 also, you went ahead and you used this edge again and you put D2 amount of demand, okay, or D2 amount of bandwidth cabling you did between S2 and T2 using a single path. Now you need only a single path per SI-TI pair in this problem. Now if you look at this edge over here, it is being used twice, both for S1T1 and S2T2. Now you being a supplier, you can go to this edge and say, well, I need to lay it like D1 plus D2 units of cabling through this edge, right? So I might as well buy it together. And that is why the star is here. You have a purchase cost for the bandwidth that you purchase on every edge. Okay. Now that purchase cost obeys these bulk properties. And what do I mean by bulk property? Well, it's not exactly linear. So if you buy 10 units plus 10 units on the single edge, it costs the cost of that is cost of buying 20 units is less than twice the cost of buying 10 units. Okay, so I'll say that make this formal in a moment. Just think of this as the cost per unit uh, reduces if you buy more on a single edge. So I will use CE to denote the capacity that is used on the edge after you route all the pairs. Okay. So formally, this is what you want to output. Okay. You want to output a part Pi for every SI-TI pair. And what is the objective over here? The objective, as you can guess, is to minimize some linear function of the cost that we pay. So for every edge in the graph, okay, you need to purchase f of CE. You need to pay f of CE amount to purchase C units of bandwidth, right, on that edge. Now, over and above this, notice that we have a length per edge. So if you want to say lay a 10 megabit cable over a smaller length, it should cost less. Okay, so we need to multiply this by the length of that particular edge. Yes. So suppose on this edge, which has length is equal to 5, you purchase like you need to purchase 10 units. Okay, so this means the cost on this edge is f of 10 times 5. Now I've not told you what f is explicitly, and we will not need the exact form of f except to know that it is satisfies the buy at bulk property. Okay, so what do I mean by that? So it means that if I buy u units, then the cost per unit of bandwidth that I've bought is going to be higher than if I purchase u plus delta. Okay, so the more I buy in bulk, of course, the quantity, the cost that I pay per unit will reduce. Now, an immediate implication of this, I claim, is that f of u1 plus f of u2 is greater than equal to f of u1 plus u2. And why is this? Well, what does this statement over here say? It just says that if I buy 20 units in bulk, it costs more than buying 2 cables of 10 units. And the reason this holds is you just replace the above, the delta by u2 and u by u1 and vice versa. Okay. So proof of this particular claim is the following. u1 is greater than f of u1 plus u2 by u1 plus u2, right? And f of u2 by u2 is equal to f of u1 divided by u1 plus u2. And now if you transpose and add, the u1 plus u2 will cancel out. You can just check this and will give you the result. Okay, so this is the kind of important form that I want you to keep in mind. Now, an immediate first observation about this is the fact that if the input graph is a tree, then the problem is close to trivial. Okay, by is it close to trivial? Whereas because let's say this is my tree, okay, and then you have S1 and T1. I wanted to route demand D1. Well, the only way you can route it is via the unique path that connects S1 and T1. Okay, so you will purchase D1 units of demand along this whole path. Okay, and now suppose you had say S2 here and T2 here, you would similarly buy D2 units along this path. Okay, and so if you had just these two pairs, then the capacities that you need to buy on the edges of the tree are kind of fixed, because on all of these edges you need to buy just D1, and just on this edge you need to buy D1 plus D2, and on this edge again you just need to buy D2. Okay, so you know the capacities exactly, you know what is the purchase cost, you can optimally find the solution. Now, if the input graph is not a tree, that's when we are in the general case. How do we solve this problem? Well, given what I've told you before, the intuition should be kind of clear. So from G, we go through a tree, okay, while keeping distances close. We solve it on this tree, and then you map back the solution in some way to the graph. Okay? And we'll have to prove a couple of things about the way we map back solutions and how it compares to the optimal in the graph G. And because we can really solve this problem on the tree without writing an LP or anything, we'll not really involve LPs at all in the solution to this problem. We will just try to move from G to the tree and solve it in the tree as I've stated, and then move back that solution. So the first step in the algorithm, as I've mentioned, is to find a tree metric. And it's on the same vertex set, but the distances, we'll call it as T prime, that approximates the distances in the graph. Next, for each path between vertices in G, sorry, I wanted the other way around. For each XY pair in the edges of T prime, remember that T prime corresponds to a tree and it has edges. In fact, I'll just call it this. Okay, for each XY which is an edge in T prime, you find the corresponding shortest path Pxy in G. Okay, clearly the weight on the edge of T prime on the edge xy will be somewhat close to the corresponding path length in G. Okay. So I just want to find this corresponding. By find, I mean keep a track of it. We'll come back to use it in a moment. So within T prime, now I know for every Si comma Ti, what is the unique Si Ti path, right? So I let okay, so let me call this path SITI. Basically, SITI, as I mentioned, there is some path in T. And this path is unique, so I don't have to think much about it. And now if you take this path between Si and Ti in tree, it is a concatenation of edges in the tree. So this path here is going to look like Si and then maybe x1, x2, so on until xr minus 1, and then finally you get Ti. Now each of this adjacent edges in the tree corresponds to a path in G. So the path that you will choose in G prime for routing from Si to Ti is the concatenation of paths xy in G for all xy, which is in this SIT. Particularly two paths in blue, and you concatenate all of them, you get your final path. Okay, and of course we are going to do this for all I. And finally, how much do we purchase on each edge in the original graph? The capacity purchased is just going to be the sum of all demands that use that particular edge. Okay, so this is a very natural algorithm. You just look at the paths in the tree T prime and for every edge here corresponds to a path in the original graph possibly. So you use that path, okay, and then you concatenate all of this. So how do we go about analyzing this algorithm? Well, the key point to just keep in mind when you're doing it is that there are two different worlds. Okay, one that we are interested in, which is the graph, and the other that we are working on, which is the tree. Okay, both happen to be metric spaces. So here's my graph G, on which I have what the algorithm outputs and what is the optimal. Okay, now there's a corresponding world T prime. Okay, and what I've managed to do is basically translate the instant G into T prime, and I've solved it on T prime. Okay, and somehow what I've described above is a way to map the solution in T prime to the solution in the graph. Yeah. Now what we want is that algorithm is less than something times opt in G. Okay. What we would like to show in order to do that is to somehow map the solution opt in G to some solution. Let me call this sol, okay, which is the map or the mirror of opt in T prime. So if opt uses some paths, I will find some corresponding paths in T prime of comparable value. Okay. And we'll use the value of this sol, we'll relate the value of sol back to opt in order to solve this problem. So this is what we are going to show as the first step, that the cost of alghat translated, okay, so the tree solution translated to the graph only goes down. Now the second thing that we'll show, cost of the solution mapped sol as indicated above is at most order log n cost of opt. Now it's important to kind of make it clear where these costs are computed. The cost here for algorithm is of course computed on the graph G, and the cost for alghat is computed on the tree T prime, right? The cost of sol here is again computed in the world of T prime. The cost here of opt is computed in the world of G. Right? All we know is that T prime is close to G in terms of distance. Okay, but otherwise T prime is an instance of the Bayes bulk network design problem, and G is another instance. Okay. So now why does this give us an order log n approximation? Well, if you think about it a bit, it should be clear. The important point to note is that the alghat that we do here is the optimal solution of the problem in the graph T prime, okay, that is in the tree. So now that's going to be an important part. Why this gives a approximation, because we do know that is less than T prime of alghat, which, because it is optimal on the tree T prime, is at most cos T prime of sol this we know is order log n time cost of opt. Okay, so it's just a chain of inequalities, and if you stare at it for a moment, you will realize immediately why it is true. So again, just keep in mind the main picture over here, that there are two worlds G and T prime which are close in distances, and we are trying to map solution from one world to the other in order to compare it. talk about on talking about maps between the two worlds, there should be some sort of direct translation that we'll use, and we need to introduce some notation for it. Okay. In particular, what we'll see is that what we'll keep using is that suppose you have an edge UV. So let me just write it. In G there's something, and in T there is something. So you have an edge UV in E, and this translates to a path P prime UV, which is unique in T prime. And similarly, if you have an edge then this translates back to a path in the original graph. I'll call that as TXY G, and it's a path, so I'll think of a path as a set of edges. And further, in the T prime world, when I'm solving the algorithm, I use some capacities on the edges. And this is in the optimal solution in T prime, because we translated the instance to T prime and we can solve it optimally here. It uses some capacities. So notice that the above mapping also gives you a mapping between paths in G to paths in T prime. Okay, maybe not simple, not simple paths, because if you have a sequence of edges constituting a path in G, okay, then you have a corresponding path in T prime, which consists of the concatenation of the paths corresponding to each of these edges. For the distances in T prime, I'm going to denote by T prime x comma y. The distances in G I'm going to denote by d of xy, which corresponds to the shortest path. Okay. Now the xy adjacency, this has to be one of the shortest paths. Now the first lemma, as I said, is going to be the following. That my final algorithmic cost is at most the cost of the, what do I mean? This is again, if you recall, it is the optimal solution that we found in the tree T prime. And given that C prime xy's are the capacities that we needed to purchase, we can immediately write this as summation over the edges. Right? You have T prime of xy times of C prime xy. So this is by definition over here. At this point, it might be useful to recall how T prime relates to D. We know that T prime xy is greater than or equal to D of xy. And when I said you find a T prime that is close to the distance, then what I meant is that in expectation, so T prime is going to be random. So the expected value of T prime of xy is less than or equal to mod log n D of xy. and this is not this can be any UV. Okay. So keep this in mind, and using this, how do we prove the lemma? Well, recall that for every edge that was there in T prime xy, so let me start with every demand pair SITI in the tree T prime, there was a unique path, and for each of these edges, we found the shortest path. So if there was a xy here, we found the shortest path in G and mapped it, right, between Si and Ti, and all along this was the concatenation of certain paths corresponding to the edges, adjacent edges in the tree. Okay, on each of this, we purchased corresponding amounts of capacity. Now, the only thing that we need to be careful about in these segments of paths x, y, and g is that suppose you picked a single edge E, U, V, and G, and you had an xy shortest path translated from an edge in T prime using this, and it asks you to purchase some C1 amount of capacity. Okay, and then you had some x prime, y prime path also going through this edge E, and it asks you to purchase some C2 amount of capacity on it, then you're going to purchase both of these together. So in some sense, the cost is only going to go down. Okay, so we'll see this formally in a moment, but basically you will use that. Suppose this asks for C2 capacity, this asks for C1 capacity, because f of C1 plus C2 is less than equal to f of C1 plus f of C2. When you translate the T prime cost into the graph, it just goes down. So formally, this is what's happening. You start with the right hand side, which is the cost in T prime of hat, and now this is equal to the summation of T prime edges in T prime of xy, f of C prime of xy. This is by definition how much you purchased on the tree. Now this is greater than equal to, and this is by the metric property. So these are just edges in T prime. Okay, what I mean by in T prime. Right. Now this is the distance between xy, and this distance is in the graph. And this because the distances in the tree dominate the distances in the graph. This again, I'm going to split it up as the sum of all the edges in the path on xy of LT. So this is by definition. And this seems to make it closer to what we'd like. And now I can switch the order of the summation and say that we'll look at every edge in the graph. Its coefficient appears with LE. And then what you have in this summation within is all those pairs of vertices which are edges in T prime such that Txy has E. Okay, what do I mean? That you look at these edges in T prime such that the edge E that I'm looking at was included in the shortest path in the graph G. And for each of these, I'm going to sum up f of C prime xy. This we know by Bayet bulk property is at least this quantity here, and this we know is exactly the amount purchased in our solution. So although this might seem a little complicated the way it's written out, if you think about it for a moment, it's just a simple application of the fact that you're concatenating paths together by translating them from T prime to G. And here we have used the metric property here that the distances in T prime are at least the distances in G. Now, there's also reverse translation. If you remember the picture that we had before, this is what we solved on the tree T prime and translated it to the graph G. Now there was an optimal on the graph, and we wanted to somehow translate this to some solution on T prime. Okay. So the map from optimal to T prime is also equally simple. So for every edge E, we just okay. So suppose the star was the optimal. So now every edge here corresponds to a unique path in T prime, right? And so you put CE amounts of capacity on that unique path. Purchase C capacity on path, and if you recall the notation I had used over here, I'd call this as P prime of UV. And this should be CE star. Now this has given us a solution to the same instance on T prime. Okay, and of course this is not the optimal solution because we have somehow lifted it from a solution in the graph metric. And therefore what we can immediately conclude, so call this solution sol, and then what we can conclude that cost of sol, as I said this already before, is greater than equal to the cost both in T prime. And it's because we solved it optimally on T prime. Now again, the last thing to relate is how does cost of sol relate to the cost of the optimal solution in the graph G. And that's what we'll show next. Okay, that it's within an order log n. Okay, so to prove this, the first thing is to write down the cost T prime of sol explicitly. Okay, and to do this, just recall how we translated from the optimal solution in the graph. So by definition, almost this is for every xy which is in the state of T prime. This is T prime of xy times, and over here, how much they purchase on this? Well, you look at every edge in the original graph. such that um, in the translated path in T prime xy lies, and then you add T star. Okay, so for every such edge I used xy, and hence I will be installing that much capacity in sol. Now this thing we're going to use again the buy at bulk property. Proper bound this by T prime of xy, and summation, I'm just going to say this edges of C. Well, I should say here that E is equal to UV over here. Now just flip this over and say that E is always equal to UV. I got F of E star coming out, and then I have a sum over all edges which occur PV path P prime of X. Like this is an exact equality over here. Finally, this, as we know, is nothing but there's a unique path in T prime, and so this is just the distance between U and V in T prime. And now T prime was random, so this means that, and I should modify this lemma to say that the expected cost, because T prime is random, less than equal to the summation over E, where E is F of C star, expected value of T prime UV, and from triggering property we know that this is at most order log n times LE, okay, which is also D of UV, the length of the edges. So in effect, what this has given us is our order log n approximation algorithm for the buy at bulk network design problem. While there were a lot of parameters that are involved in this problem, like there is the F, there is the capacity you want to buy, there are the lengths on the edges. The key idea behind all of it is just that you have a tree metric which is really close to your graph metric, and you can map solutions to and fro between the graph metric and the tree metric while not losing very much in your objective values, okay? Because the pairwise distances in the tree metric are preserved close to the original graph metric. That's the key idea, and if you go over it a little, it's not really all that difficult as it might seem on the first reading, okay? So with that, I want to kind of end this part regarding the use of metrics in approximation algorithms. And what we're going to do for the last two lectures on Monday and Thursday after is hardness of approximation. Now that's a really interesting topic which could take up a whole course by itself, but we are just going to get a window into how does one go about proving that certain problems are hard to approximate. Okay. So those are really interesting things to look at, and we'll see that next time.